I realized if I just take n plus 1, that's the same thing as just multiplying it by n times n factorial, kind of.
Right, right.
So I probably could have worded it that way, and would have made things a lot easier.
Well, that's good. So yeah, there's usually different ways to approach these problems.
Did we do an attendance thing already?
No, let's go ahead and do one. We're still missing about a quarter of the class, but we'll do a ping and we'll do another one later.
So I just want to clarify, when we do the attendance thing, do we just need to do it once we are connected to Zoom?
Well, so here's the theory of it, right? What I intended to do was take a few attendance pings during the class at kind of random intervals, and then go through and make sure that at the point that I asked for a ping, people responded. Because what I found happening is people at the start of class hop into Zoom, go off and work on laundry or do other homework and stuff, and then at the end of class they log off from Zoom. But I haven't gotten that sophisticated yet, so it's kind of working so far. Like, you know, as long as I get a few pings from you in response to my requests, I'm not really like looking to see if you came in 15 minutes late and sent me a ping. You're still getting credit for it. And, you know, I'm not looking for excuses to take away points from people. I just want to sort of add some additional motivation to make sure people try to come to the class and stay in tune, you know, for the entire class. So, you're only required to send me a ping when I ask for it. But, you know, if you come in late and you send me a ping that I didn't just ask for, you're probably okay. I mean, it lets me know that you were here at least for part of the class.
Gotcha.
And I don't know what I'll do next quarter. I'll come up with something else.
Right. Out of curiosity, how would I do number 8, the factorial problem in 3.5? How would I do that with the what's it called, inequality?
So I'd rather not go over the details of these problems today, because a number of people are using a slip day and are going to turn it in tomorrow, and I don't want to sort of, you know, just blanket give out the answers to people.
Okay.
If people come to office hours, I'm pretty much talking them through the process anyway. But then at least, you know, we can have some back and forth and so on. So my plan is to go through the homework on Friday. I'll grade it today or tomorrow and post grades with feedback, and then we'll go through the problems in detail on Friday.
Yeah, I understand that. That makes a lot of sense.
Okay. And yeah, we can go through some examples of induction problems today that might be similar to the homework. I'm guessing most people are asking about the factorials or the inequalities, or both. And yeah, we can talk about some things related to that.
Yeah, the inequalities were interesting because you can pretty much substitute one side for something that you know is less than that side, or greater than, and that made it kind of funky for me. That hurt my brain a little bit.
Yeah. So inequalities, when I learned these in school, they kind of weirded me out because they don't always make intuitive sense to me, at least. But, you know, if we're thinking of just plain old integers, and we know that a is bigger than b, then one thing we can always do is we can add the same thing to both sides. We can pick any number c, positive, negative, 0, and we know that a plus c will be bigger than b plus c. So, you know, put these on a number line. A is to the right of b. When we add c, we're just moving both things over by the same amount. That inequality is going to be preserved. We can also say, you know, if p is some integer bigger than 0, then we can multiply by p and still have that same equality. Same inequality. So if a is bigger than b, 2a is definitely bigger than 2b. In fact, it's even more bigger than A was bigger than B. But if you do this with a negative, it flips. Sorry, say again?
In that case, C doesn't matter.
Yeah, C is just an integer.
Okay. Because I did do that on one of mine, and I didn't know where else to go with it. And I was like, well, if you got 4A and 2B, then 4A is always going to be bigger than 2B no matter what.
Mm-hmm.
And that was kind of my proof, but I wasn't sure if I understood that correctly.
So, for example, if A is bigger than B, then we know that 2A is bigger than 2B because we can multiply by positive integers. We also know since 4 is bigger than 2, assuming that A is positive, 4 times A will be bigger than 2 times A. And so we can put this and this together and say 4A is going to be bigger than 2 times B. And that should work.
Yeah, I think one of mine ended up as like 6K plus something is bigger than 4 of a different integer plus something.
Mm-hmm.
Okay.
So if A is bigger than B, and 20 is bigger than 5, we can definitely say 20 plus A is going to be bigger than 5 plus B. So these inequalities preserve nicely, but this is really just saying, A is bigger than B, so 20 plus A is bigger than 20 plus B. And again, since 20 is bigger than 5, then 20 plus B is bigger than 5 plus B. And so we can take this and put them together transitively and say 20 plus A is bigger than this thing, which is bigger than 5 plus B. Right? And so this really falls out of that.
That's what makes this topic so interesting right there.
Mm-hmm. Inequalities are really powerful. They pop up in interesting places, like for example, Goldbach's conjecture, which says, every even integer can be written as a sum of 2 primes. So 4 equals 2 plus 2, 40 equals, 3 plus 37, 42 equals 5 plus 37. And this conjecture is that you can do that for every even integer, 4 or bigger. And nobody's proven this, but they've proven, that if there is a number for which this doesn't work, it's bigger than some ridiculously big number. And so a lot of times when you're trying to prove something, you can prove it for numbers, that have certain properties. Or you can say that an exception to this would have certain properties. And sometimes it feels like inequalities are easier to work with because, they're not as demanding as, equality. How did I get 5 plus B here after 20 plus B? I use these two properties. 20 plus A is bigger than 20 plus B, and 20 plus B is bigger than 5 plus B. So this is this general thing, if X is bigger than Y, and Y is bigger than Z, then X is bigger than Z. There's 5 plus B, there's something bigger, there's something even bigger. Let's see, will 223 have a remote learning option? Yes, so CSE215 in spring, there will be one section that's remote and one section that's in person. That's the current plan. Alright, so factorials, n factorial is just, product of all integers. up through and including n. And when you're working with factorials, sometimes it's useful to write, you know, the first few terms of this expression and the last few terms. And, you know, I didn't have to write the n minus 1, but sometimes it's useful to write that. And so if I've written n factorial like this, I can think about n minus 1 factorial. And that's 1 times 2 up to n minus 2 times n minus 1. And having written these things in this manner, I see, for example, that this and this are the same thing. And that might lead me to note that this thing is equal to n minus 1 factorial times n. And that's a really useful identity when trying to prove things that involve factorials. So n factorial is n minus 1 factorial times n. Equivalently, n plus 1 factorial is n factorial times n plus 1. And you know, you can do algebra on these things. This is n times n factorial plus n factorial. So there's another way to get the next factorial. Take n factorial, multiply by n, and then add n factorial to it. What else might be useful here? Other than that, just keep in mind algebra. Try to factor things. If you have something like this, distribute. Try to multiply it out. And then maybe group common terms and factor in a different way.
Yeah, that's what I found kind of interesting when we were doing like the n times n plus 1, n plus 2, or whatever that one, however that one was set up. Was it was weird to factor everything together and then set it up in a way where you can pull stuff out of it. You know, as a separate factor of like 3 or whatever.
Yeah, yeah.
That was where it kind of got a little weird for me, which was cool because you start looking at it in a different way for all the other functions. You know?
Yeah, totally. Cool.
I got there in kind of a roundabout way, but I eventually got there.
Okay.
Trust me, my notebook is just scribbles and all sorts of stuff right now. Luckily, you know, did in the notebook and then transferred it nicely to the homework table.
Yeah, that's what's nicer about homework than tests is you have the option of figuring it out and then writing it up. Which actually, by the way, is like a really good way to get more out of the homework. Because, you know, figuring it out is kind of this hodgepodge of try this, try that, let's go down this path, let's back up, go some other way, let's forget about all of that and do this other thing, right? But when you find the pathway to where you want to get, and then you try to recreate that cleanly from beginning to end, that sort of like helps, you know, solidify in our minds what the steps were that actually got us here. And you know, brush aside the missteps and false starts and so on, and that really helps with, you know, sort of building the intuition for doing these kinds of things, writing the stuff up cleanly after you've seen how to do it. And for some people, that's like actually a really enjoyable process. I'm one of those people. There's something nicely ordered and controlled about it. Well, I'm just like...
I was excited that it was figured out.
Yeah, totally. Alright, so I'll grade those over the next couple of days, post feedback, and then we'll talk about them Friday. Reminder, there's no classes tomorrow. Thursday is Veterans Day. It's a Clark holiday, so there's no classes anywhere. That doesn't affect us because we don't have class Thursday, but I thought I'd mention it anyway. But also I don't have office hours tomorrow morning, and those will resume on Friday. So homework 7 is posted, and it's back to the original textbook, and it's some questions from chapter 1. And so these are related to, you know, the product rule, the sum rule, pigeonhole principle, and then permutations and combinations, which we started talking about on Monday, and we're going to continue with those today. I could be like anybody right now. There's no way to identify me because the sun is like blinding. All right, so any questions on what we were doing before? We'd started talking about permutations, ordered combinations of ordered arrangements of objects. I gotta close. I hate cutting out the sun, but. Alright, that works better. Alright, so let's keep talking about permutations. So a permutation is an ordered arrangement of objects, and our permutation is an ordered arrangement of our objects. And we looked at some examples of this, and we came up with a formula which says the number of R permutations of n objects is given by this nice little ratio of factorials, n factorial over n minus r factorial. And so, for example, if you have 52 cards and you're trying to pick 5 of them, and suppose the order of the cards makes a difference, right? So if you're playing poker, the order of the cards doesn't matter. But suppose, you know, you've got 52 cards, you're going to take 5 of them, and the order in which you get those 5 cards is significant. So the number of ways that you can get 5 cards out of 52, that would be just P52, comma 5, which is 52 factorial over 52 minus 5 factorial. 52 factorial over 47 factorial, which will be 52 times 51, 50, 49, 48. If we don't care about the order, then we're talking about something called a combination. We'll come to that in a little bit. But for now, we're just thinking about order. If you want to know the total number of ways that you can arrange a deck of cards, that's saying I've got 52 cards and I want to pick 52 cards from that deck and put them in a particular order. And our formula says this would be 52 factorial over 52 minus 52 factorial, which is 52 factorial over 0 factorial. And we mentioned at the end of class on Monday that this is actually equal to 1. And so this is 52 factorial over 1, which is just 52 factorial. And the easiest explanation of why this is equal to 1 is because it makes things work, right? We know that if we want to pick 52 cards, we could break that into 52 subtasks. We can do the first card 52 ways, the second card 51, and so on. And so this should be the number we end up with. And so this has kind of got to be equal to 1. But we can also look at it as this thing that we mentioned, which was the gamma function, which you don't have to know about, but it's a cool thing. So 0 factorial is 1, and that makes this thing work correctly. Just as a kind of other edge case, suppose we say how many ways can I pick 0 cards from a deck of 52? How many different hands can I end up with? And if we just plug into our formula, this would be 52 factorial over 52 minus 0 factorial. 52 factorial over 52 factorial, which is just 1. And so
you don't take any cards, you end up with one card?
no, you end up with one hand that you can end up with, which is an empty hand.
Okay.
All right, so that's kind of a sort of edge case, but it works. And if you try to draw one card, you got 52 cards in the deck, and you're going to take a single card. How many different hands can you end up with? 52 factorial over 52 minus 1 factorial, which is 52 factorial over 51 factorial, which if you multiply it out, everything will cancel except that 52. And that's sort of what you'd expect. If there's 52 cards and you're picking one card, how many different ways could you end up with you know, a hand of a single card? Well, there's 52 options. Sorting 52 cards, illegal in nature. Interesting. All right, and sometimes we'll get questions where we need to think differently about what we're being asked to do. So, for example, how many ordered arrangements of these first 7 letters contain A, B, C side by side? So if we've got 7 letters and we want to know the number of ways that we can arrange those, that's just plain old 7 factorial, right? That's just, you know, 7 things, we're going to choose 7 of them. That's P of 7, 7, which will just be 7 factorial. But if we're interested in only arrangements where A, B, and C end up next to each other, that's a different kind of question.
Are we saying that it's A, B, C specifically, or it could be any arrangement of A, B, and C as long as it's A, B, and C?
No, it's got to be A followed by B followed by C.
Okay, then wouldn't we treat A, B, C as a single item, and then do the factorial slightly differently?
Yeah.
Saying that, well, now there's no longer 7 items, we're going to say that there's 5, because A, B, C is now a single item, and then
Perfect.
factorial out of it.
So we can rephrase this question as how many ordered arrangements are there of these things? Right? We've got 5 objects, A, B, C, D, E, F, and G. And any time that we rearrange those, A, B, C will be next to each other. And any arrangement of these where A, B, C are next to each other will be an arrangement of these 5 symbols. And so the number of ways we can choose 5 things and arrange them 5 of them is just going to be P5, 5, which is just 5 factorial. So that's a cool little example where by kind of stepping back and rethinking the problem, we can use the exact same formula we already know. It's just applied to a different way of looking at the problem, right? And that's what, you know, this year at Clark is all about, right? It's about finding different ways to look at problems so that you can solve them using what you know. So that's a cool example of that. All right. So the other version of this is what we call a combination. And a combination is an unordered arrangement of objects. And the only way I know to remember this is it's kind of intuitively backwards. Because, you know, a combination lock, the order matters. But combinations are unordered things. So, but, you know, put it down on a note sheet somewhere. So, and our So a combination is an unordered arrangement. And so we can talk about Cn comma R, which is an R combination of n items. And basically you've got n items, you're going to pick R of them, and it doesn't matter what order you pick them in. So for example, you have 4 people, and you want to choose 3 to win a prize. And the prizes are all the same. It's not like first place, second place, third place, right? Each person gets, you know, a movie ticket, and the prizes are identical. So how many ways can you award these prizes? Well, how many ways can you choose 3 people from a set of 4 if we don't care about the order of them? And so this is what C combination refers to. CNR is the number of R combinations of n items. And let's think about the playing card example. So you have 52 cards, and you pick 5. And if we pay attention to the order, right, so if my cards are an ace, a jack, a 10, a 7, and a 3, right, if we're paying attention to order, it means that if I pick the cards and they come out like this, I'm considering that to be a different situation from where, say, I pick an ace, and then a jack, and then a 10, and then a 3, and then a 7. Right? So when we're paying attention to order, when we're talking about permutations, we have P 52 comma 5, which is 52 factorial over 47 factorial. If we're talking about a combination, we're saying that we're treating this and this as the same. And we're also treating this as the same. And we're also treating this as the same. And you know, as long as we pick the same 5 cards, we're considering it the same combination. So here's a sub-question. How many ways can we arrange these 5 cards that we picked? So first I'm going to pick 5 cards from the deck. And let's say I picked an ace, jack, 10, 7, 3. How many ways can I rearrange 5 cards? And we already know the answer to this. Yeah, there's a total of 5 factorial. And so this is the number of hands that I can pick if I consider each of these to be different. Right, but for any set of cards that I pick, I'm counting 120 5 factorial. I'm counting 120 arrangements as being distinct. So if I take this number of permutations and I multiply by 1 over 5 factorial, that should give me the number of combinations. In other words, I divide out the number of ways I can arrange the cards that I pick. This will give me the number of unordered arrangements. And so that's kind of a hand-wavy motivation for a general formula, which is C of n comma r equals n factorial over n minus r factorial times r factorial.
You have like an array of stuff like that.
Yeah, I just noticed that.
It's hard to see.
I could write, like, you know, special secret information down here. Where's that coming from? Nope.
So this is the formula for order, you said, right? Order combination.
So this is for unordered.
Or unordered, okay. Oh, okay, and then ordered is the same thing, just minus the r.
Yeah, so Pn comma r is n factorial over n minus r factorial. And that's the number of ordered arrangements. And intuitively, if we're paying attention to order, we've got more possibilities. So back to this example, here's 4 pens. How many ways can I choose 3 pens? Well, I could choose those 3, these 3, these 3, or these 3. There's only 4 possibilities. But if I pay attention to order, I could choose these 3, I could choose those, I could choose those, I could choose those, and so on, right? And so you're going to get a lot more ways that you can choose an ordered arrangement. And so this number is bigger than this one, and it's bigger by exactly, r factorial times.
Can you show that previous page that kind of helped us see the intuitiveness of that?
This one?
Yeah.
Yeah. And we can let's do a full example that uses that same principle. So suppose we start with the letters A, B, C. And we want to find the number of ways that we can choose 2 letters out of 3, paying attention to the order. So what sets of 2 letters can we get from here? So start shouting some out. And we're paying attention to order. A, B.
A, C, B, A, C, A.
E, B, A. Only sets 2. So.
Yes, that's a 2. That's okay. There's still more.
CB.
CB, good.
And then BC.
And BC. And I think that's it. So this should be equal to 6, right? This is 3 factorial over 3 minus 2 is 1 factorial. That's equal to 6. So we've got 6 ordered arrangements. Okay, now if we want combinations, right, our rule tells us this should be 3 factorial over 1 factorial times 2 factorial. That should be only 3. So what are some of the pairs of letters we can choose from A, B, C?
Would just be A, B, A, C, and B, C.
And that's it, right? So we did A, B, we did A, C, and we did B, C. But B, A, gets us the same thing as A, B, C, A gets us the same thing as A, C, and C, B gets us the same thing as B, C. The fact that we had pairs of these things that were all the same, that's what this 2 is coming from. And so if we did this with, number of ways to pick 3 things out of 4, we would find that we had 6 things that were the same set of letters, just in different arrangements. And so if we glom those together, we get a smaller number of combinations. And it's smaller by exactly that factor. So that's a more specific example of what we were doing here. And there's a bit of notation here. And you're going to want to be careful with this notation. C3 comma 2, or more generally Cn comma r, we sometimes write this as just nr inside parentheses. And this is not n divided by r. There's no horizontal line here. This is not any symbol that we encounter in algebra normally. It's a completely new type of terminology, right? A pair of parentheses with two numbers, one written on top of the other, is a shorthand for C parentheses n comma r. And it's just a form of notation that we're going to use in this class. It pops up a lot in statistics classes because statistics talks a lot about permutations and combinations. All right, so let's do some examples. So, well, we'll start with the poker hand, 52 cards, and we want to pick 5. And when you're playing poker, the 5 cards in your hand, it doesn't matter in what order those cards were given to you. The only thing that matters about your poker hand is the actual cards themselves. So the number of ways you can pick 5 cards out of 52 is just this. And we call this sometimes 52 choose 5. And so we'll call this sometimes N choose R. And so you can think of the C as being choose as well as combinations. So 52 choose 5 is 52 factorial over 47 factorial times 5 factorial. And if you want to calculate this, you can do it by hand pretty easily. You don't really need to find 52 factorial because we know 52 over 47 factorial, most of those things are going to cancel. This will be 1 through 47. This will be 1 through 47 times 48, 49, 50, 51, 52. And then we're going to divide by 1 times 2 times 3 times 4 times 5. And we can actually calculate this pretty easily. So I can take the 5 and the 2. That gives me 10. I can cancel out with a 50 and make this a 5. And the 3 times a 4 is a 12, and 12 goes into 48 4 times. So this is going to be 49 times 51 times 52 times 20. And it's not that big a number to calculate. I still used a calculator. 2,598,960. So that's the number of ways you can get 5 cards out of 52.
Are you okay with us using like the TI-84?
Yeah, although when you're doing a test or even doing your homework, in a lot of cases formulas are better than numbers as far as partial credit. So let's say I gave you a question and I said, you know, how many ways can you pick 5 cards out of 52 if order does not matter, right? You definitely want to make sure that somewhere really easy to see on your answer sheet, you've done this, right? Or maybe this, right? Because that tells me you understand that this is a combination as opposed to a permutation. That's half the problem right there. You've got a bunch of points just for putting that down. And now if you say something like equals 52 factorial over 47 factorial times 5 factorial, you got a bunch more points because now I know that you know the formula for calculating a combination. And now, you know, you type this into your calculator or you do something and you get the number wrong, you might not lose any points because that's a math error and I'm not worried about math errors, right? On the other hand, if you do this in your head and you calculate this and you plug it in and you write down this number and there's none of this stuff here, you might not get credit, right? So for questions like this, you definitely want to make sure that you're showing your work, right? How you got to the answer. And that's generally worth more than the actual answer itself at the end of it all. And on a test, you know, if you get this far, I'll try to specify it, but I would probably be perfectly happy with that and not having you take it any further. Because, you know, that's just plug and chug.
Okay.
All right, so let's look at an interesting thing about combinations. Suppose you've got 10 people, and you're going to choose 7 to, I don't know, win a prize, go on a trip, something, right? So you want to choose 7 people out of 10. How many ways can we do that? It's just 10, choose 7. And our formula tells us this is 10 factorial over 3 factorial times 7 factorial. So I've got 10 people and I want to choose 7 to go to lunch. There's an identical way to think about this question, which is if I have 10 people, I could choose 3 to not go to lunch. If I choose 3 people not to go to lunch, I've chosen 7 people who will go to lunch. It's the other 7. If I choose 7 people to go to lunch, I've chosen 3 people not to go to lunch. It's the other 3. So the number of ways I can do this should be exactly the same as the number of ways I can do that. And if we use our formula, 10, 3, it tells us this is 10 factorial over 7 factorial times 3 factorial. Guess what? Those are exactly the same thing. So there's a symmetry to these choice functions. 10 choose 7 will be the same as 10 choose 3. 10 choose 2 will be the same as 10 choose 8. 10 choose 6 will be the same as 10 choose 4. And we'll see a beautiful form of this in a little bit.
I can't restrain myself from drawing a fraction instead of that.
Yeah, I know. We keep wanting to put a slash in there. And if that's, you can always do this. That's perfectly acceptable. But sometimes you'll see this, you just want to know what it means. But you can always change it into this when you're writing it up. Man, that streak of light is kind of relentless. And that's where it's coming from.
A lightsaber's coming across your
I know, right?
work there.
I'm going to game the system, though. Yeah, that's pretty good. Nope. Hey! You got a solution?
Nope,
Oh,
not yet. I'm working on it.
okay. Thinking if I turn it the other way. Oh, that's bright.
You getting lines?
Getting one really, really fierce line. And it's coming from right here. I think it's just reflecting.
I have a temporary solution.
Yeah? Okay. Oh, yeah, I got one too.
Just open them all up and see if the camera adjusts just fine.
My CPU is gonna catch fire. Oh, that's a serious solution.
What is that, like 27 blinds to shoot?
Yes, exactly. Hey, that works pretty well. And it's a cooler background. All right, so there's the symmetry between. Sorry?
So exotic.
Yeah, right? There's a symmetry between n choose r and n choose n minus r. And it's basically, you know, choosing R things to include, choosing R things to not include, or n minus R things to include. Alright, so we haven't looked at a weird example in a while, so let's look at a weird example. How many n-bit strings contain R ones? So let's think about 4-bit strings. And what are our 4-bit strings? We haven't done this since Engineering 250, or I haven't done it since Engineering 250. So we'll write out all the 4-bit strings that we know. And have you ever thought about this before? Like, how many of these strings contain exactly 3 ones? I don't know. Haven't really thought about it. But like, suppose we want, you know, to find the strings that contain 3 ones. So there's a string, there's a string, there's a string, there's a string. Looks like 4. But we could answer this question, how many 4-bit strings contain 3 ones, by using this notion of a combination. And so the way we think of this as a choice question, go ahead.
These are exclusively 3 ones, right? 'Cause the last
Yeah,
one-
exactly 3 ones.
Okay.
Yeah, so not that one. So how can we think of this as a choice question? Any ideas?
Well, we could do 4 factorial over 3 factorial, or excuse me, over 1 factorial times 3 factorial.
So what does that represent intuitively? In terms of choosing things? Or where did that come from?
So that's going to be all. So 4 factorial is our number n, right? How many different combinations we can pick, right?
Mm-hmm.
And then r is how many things with that combination in our total combinations, right?
Okay. So let's okay, so yeah, so somebody also put this in chat. So 4 options, choose 3 to be 1s. We can think of this as we have 4 bit positions. We have bit 0, bit 1, bit 2, bit 3. To create a string containing 3 ones, we have to choose 3 of these to contain a 1. And the order in which we choose does not matter. If I say I'm going to put a 1 here, here, and here, I end up with the same number as if I say I'm going to put a 1 here, here, and here. Right? The order in which I choose these 3 positions to put a 1 does not make any difference on the final number. So I'm just looking at how many unordered arrangements are there of 3-bit positions taken from 4. So this is just good old 4 choose 3. Which is 4 factorial over 1 factorial times 3 factorial, which is just 4. And that's the 4 entries that we found. If I want a number containing 2 ones, that would be 4 choose 2, which will be 4 factorial over 2 factorial, 2 factorial. So 24 over 4, this should be 6. So where are our strings with 2 ones? There's that, 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 and that. So there's our 6. How many strings contain no ones? That's 4 choose 0, which is just going to be equal to 1. That's that string right there. How many strings contain 4 ones? That's 4 choose 4, which is equal to 1. That's this string here. And by symmetry, we know that the number of strings containing a single 1, 4 choose 1, should be the same as 4 choose 3. because the number of strings containing a single 1 is the same as the number of strings containing 3 zeros. And the number of strings containing 3 zeros should be the same as the number of strings containing 3 ones. Different strings, but the same number. So this is going to be 4. Now, if I take these answers that I came up with, number of strings containing 0, 1, 2, 3, or 4 ones, and I add them together, 6 plus 4 is 10, plus 4 is 14, 15, 16, I get 16. Guess what? 16 is 2 to the 4th. Is that a coincidence?
I would say no, because you have how many different combinations there, which would equal the total number of positions you have, right?
Yeah, absolutely. If I have a 4-bit string, this is the number of strings containing 0 ones. This is the number containing 1. This is the number containing 2. This is the number containing 3. This is the number containing 4. And any 4-bit string is going to contain either 0, 1, 2, 3, or 4 ones. And so if I add up the numbers of each of these, I should get the number of 4-bit strings, which is 2 to the 4th. And so we could generalize this, and for any number n, if we add these up, we should get 2 to the n. But if we want to fill up a whiteboard with some fun-looking equations, we could also write this. And there's a beautiful little equation involving a bunch of factorials and fractions on the left and a power of 2 on the right. And intuitively, I think it's really hard to see why adding up all of these fractions of factorials should give us a power of 2. But if we think of it in a particular example as, say, you know, strings containing n bits, and these are the number of strings containing 0, 1, 2, or n ones, we know that's got to add up to the number of n-bit strings, which is 2 to the n. And so this is an example where thinking of a particular interpretation of something like, you know, a choice function can help us see something that from the math is not very obvious. Right? And a lot of times we use math to tell us something about, you know, our sort of day-to-day world. If you know, a massless cylinder is sliding down a plane at this rate, then it's going to roll this far and burst into flames, right? But sometimes our intuition about what's going on, you know, in some common experience, like number of bit strings, can give us some really interesting mathematical results. And so this is the kind of thing that's going on here. All right, so let's talk a little bit about binomial coefficients. I don't know if this is normally taught in school anymore or not, but it pops up really naturally at this point in talking about combinations. And so let's just think about an expression like a plus. Let me stick with x and y. An expression like x plus y to the n. And we know x plus y to the 0 is equal to 1, because everything other than 0 raised to the 0 is 1. X plus y to the first is just x plus y. X plus y squared, you can FOIL, you get x squared plus 2xy plus y squared. X plus y cubed, you can multiply this by x plus y and you get x cubed plus 3x squared y plus 3xy squared plus 1. And we'll do one more, x plus y to the fourth, x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. You have to trust me on that one if you don't know it. And it turns out that these are related to combinations. And in fact, this number over here, if we put in the ones in front of each of these, this 1 is actually 4 choose 0. This 4 is 4 choose 1. 6 is 4 choose 2. 4 is 4 choose 3. And 1 is 4 choose 4. And so if we know how to find these combinations, if we know how to find n choose r, we know what the coefficients are when we try to multiply this binomial x plus y to a power. Yes, we are coming to Pascal's triangle. Absolutely. So about half the time I teach this class, I do the following, and about half the time I skip the following. And I'm going to do it. And, you know, this took me a lot of thinking about it before it started to make sense. So if it doesn't make sense to you, that's okay too, right? But let me just mention this because I think at some point you might come back to it and it might make more sense and it might help with a different way of viewing combinations. Let's think about what happens when we take x plus y to the n. And if you multiply these out, what you end up with is a bunch of terms added together, and these terms always look like x to the something times y to the something times some number. And these two somethings always add up to whatever power you're raising it to. If I'm doing x plus y to the fourth, there's x to the fourth. If I have x cubed, I multiply by y to the first. If I have x squared, I multiply by y squared. 2 plus 2 is 4. If I have x to the first, I multiply by y cubed. 1 plus 3 is 4. And you can sort of see by doing some of these multiplications that, you know, if I multiply all of this by x plus y, I'll get a mishmash of terms. I might get an x to the fifth. I might get an x to the fourth times y, or an x cubed times y squared. But it's always going to be, you know, x to the something, y to the something else, where something plus something else is 5 in that case. But if you write this out, so x times x plus y times x plus y and do like a super FOIL, right? So FOIL, first, outer, inner, last. We multiply the first terms, the outer terms, the inner terms, and the last terms. Well, try to do that with like 5 terms. So first we're going to pick the first of each of these. And then we're going to pick the first of these 4 and the last of this. And then the first of these, the last of that, and the first of this. And the first of these and the last of these two. And you're going to try to find all those combinations of choosing the first and last out of each binomial. And what you'll find is that, you know, any time that I do this, and I end up with, say, you know, x cubed times y squared, the reason I'll have ended up with x cubed times y squared was because I picked the first term out of 3 of these. I said, okay, let's use the first term here, and the first term here, and the first term here. And from these, I'm going to choose the second term. Well, since I chose the first term out of 3 of these, right, when I multiply those, I'm going to get x cubed times y squared. So the number of ways I can choose the first term out of 3 of these 5, that's how many times I'm going to add x cubed y squared to my sum. And so this number that goes in front is going to be the number of ways of choosing 3 expressions out of 5. And so we get this general rule. This will be the sum from I equals 0 to n of n choose I times x to the I times y to the n minus I. And you may have seen that in a course somewhere. And this is just coming from doing a choice function.
Where exactly does this come super handy again, this specific function?
It's just a cool thing to know. We're not going to use it for much of anything, but when you study certain types of algebra, you come across this thing called the binomial theorem or the binomial expansion or binomial coefficients, and it's a rule for writing x plus y to the n as a sum of terms. Right, and if I know what my binomial coefficients look like, I can write this.
I think my calculus 1 teacher actually used this to prove power rule.
Ah, nice. And we could actually do something like that here. Suppose I just let x and y equal 1, and I say let's calculate 1 plus 1 to the n. Well, it's the sum from I equals 0 to n of n choose I times 1 to the I times 1 to the n minus I. Well, 1 to the I is just 1, and 1 to the n minus I is just 1. And 1 plus 1 is just 2. So from this general formula, we have the following fact: 2 to the n is the sum from I equals 0 to the n of n choose I. And that's that thing that we snuck up on by counting bit strings containing I ones. And so again, if we add up all of these choice functions, we end up with a power of 2. And that's pretty cool. And it's pretty cool because this leads us to one of the very beautiful concepts in math, which is called Pascal's Triangle. And Pascal's Triangle is a triangular arrangement of numbers that look like this. So we start with a 1, and then a 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. And I can keep doing this all day, right? So there's a handy trick to doing Pascal's Triangle. You always put a 1 in the beginning and a 1 at the end. But every number in the middle is the sum of the two numbers above it. So 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 and 15 is 35. 15 and 6 is 21. 6 and 1 is 7. That's the next row of Pascal's Triangle. And I can do this, you know, till the cows come home.
Can you use this for expanding out the polynomial?
Mm-hmm.
Or binomial? Oh, cool.
Yeah, so x plus y to the 8th will be x to the 8th plus 8x to the 7th y plus 28x to the 6th y squared, 56x to the 5th y cubed, and so on and so forth.
I will never foil another one of those again.
Excellent. And this also tells us, you know, the values of choice functions, because this triangle is also 0, choose 0, 1, choose 0, 1, choose 1, 2, 0, 2, 1, 2, 2. We'll see if I can avoid writing a fraction here. 3, 0, 3, 1, 3, 2, 3, 3, and so on. And so if you know this triangle, or you tattoo it on your wrist or something, right, you can always find these combinations. If I want to know what 3 choose 2 is, right, it's just this number right here. It's a 3.
So if you add up a whole row, that's basically how many different combinations you have for n items, right?
Yeah.
Or for n.
Which, by the way, we kind of know what that is. So if I add up everything on this first row, that's just a 1. If I do 1 plus 1, that's a 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 1, 4, 6, 4, 1 is 16, and so on. So if I add across each row, guess what? I get successive powers of 2. There's also this clear symmetry around the middle. So each row reflects 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 20, 15, 6, 1. And so that's kind of cool. And there's all kinds of cool properties in here.
Oh, it's only powers of 2. These are converted to the power of
Yeah.
There's stuff in between.
Mm-hmm. Let me see if I can find this cool little page here. Can't find it right now. I will look for it later. So what else can we find in here? Suppose I add up the square of each element on each row. So 1 squared is equal to 1. 1 squared plus 1 squared is 2. 1 squared plus 2 squared plus 1 squared. That's 1 plus 4 plus 1, that's 6. 1 squared plus 3 squared plus 3 squared plus 1 squared, that's 1 plus 9 is 10, plus 9 is 19, plus 1 is 20. And we can do one more, 1 plus 16 plus 36 plus 16 plus 1. Well, 16 and 16 is 32, that's 34 plus 36, this is 70. Well, this 2 is right here, this 6 is right here, this 20 is right here, this 70 is right here. So when you add up the square of elements on row n, you end up with the middle element on row 2 times n. And that's kind of cool, if nothing else. All right, if you take the number 11 and we do 11 to the 0, you get 1. 11 squared, sorry, 11 to the first, you get 11. 11 squared, you get 121. 11 cubed, you get 1,331. 11 to the fourth, you get 14,641. Well, that's what each of these rows looks like. So if you take the digits here and you write that out as a 5-digit number, it turns out to be 11 to the fourth. Which is sort of cool, right? Alright, here's one other weird property. I don't know why this one is true. Let's take, let's forget about the first couple of rows. Let's look at this row. And we're going to ignore the ones on the sides. Okay, so I'm gonna label these rows 0, 1, 2, 3, 4, 5, 6, 7, 8. I guess I'll go one more. Let's do row 9. So 1, 9, 36, 84, 126, 126, 84, 36, 9, and 1. All right. If you look at all the numbers in the middle of a row, on this row, the numbers in the middle, there's only one number in the middle, is 2. 2 is a multiple of 2. All right, so I'm going to mark that with a check mark. If we look at the row 3, the numbers in the middle, 3 and 3, each of those is a multiple of 3. So I'll mark this with a check mark. If we come down to row 4, the numbers in the middle, 4, 6, and 4, well, 6 is not a multiple of 4. So I'm not going to mark that one. Row 5, 5, 10, 10, 5, those are all multiples of 5. Row 6, 6, 15, 20, those are not multiples of 6, so I won't mark it. Row 7, 7, 21, 35, those are all multiples of 7. So we'll put a check mark there. 70 is not a multiple of 8, so I won't mark this. Row 9, 84 is not a multiple of 9, so I won't mark that. So what are the rows? Yeah, what are the rows that I've marked? 2, 3, 5, 7, but not 9. Those are prime rows. And it turns out that all the numbers in the middle would be a multiple of the row number if and only if the row number is a prime number.
That goes back to the theory that all numbers have a root prime, right, basically?
That's probably related to that. This one I really do not understand where this comes from. I will play around with it someday, perhaps if I find myself stranded on a desert island, or if I take a vacation someday, because this seems really cool. And you know, remember, these things are factorials. These are ratios of factorials, but they're also simple additions, right? I can find the 10th row by just adding up pairs of consecutive things on the 9th row. And so it feels like there's some sort of link there that that might be exploitable for testing primes or generating primes. And primes are one of these things where they lead to so many different things. You play around with primes and you find remarkable properties about complex numbers, or vice versa. And it's just a really sort of rich sinkhole that you can fall in. Let me see where my cool properties of... Well, maybe I didn't save it. Maybe I just bookmarked it. My cool properties of Pascal's triangle. Oh boy, my Clark page is a mess. Pascal's triangle. So this is from University of Georgia. So there's Pascal's triangle. So there's the prime thing, right? So primes are rows where each number in the middle is a multiple of the row number. Powers of 2, when you add up across each row, you get a power of 2, and we've seen a couple of reasons why that would be true. Magic 11s, so these are 11 raised to different powers. And then the hockey stick pattern. So if you move down and then at the very end you make a little jog in the opposite direction, what do you end up with? Oh, the last number will be the sum of all the other numbers on this diagonal. So that's kind of cool. Your triangular numbers, sums of consecutive integers, those fall along this third diagonal. So 1, 1 plus 2, 1 plus 2 plus 3, and so on. And so that's, you know, n times n plus 1 over 2, which we know from induction proofs. And a lot of these characteristics, right, you could prove using mathematical induction. Right? When we've seen that, you know, adding up a row of Pascal's triangle gives us a power of 2, we can see that by saying, well, if we have a 5-bit number, right, how many of those bit patterns contain 0 ones, a single one, 2 ones, and so on. We can generalize that to n bits by using mathematical induction. Right? So we can take what we've already done and spin it that way. So square numbers, down the diagonalist picture to the right, are the square numbers. You can find them by summing two numbers together. plus 3. Oh, okay, cool. So, so 0 plus 1 is 1, 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10 is 16, 10 plus 15 is 25, and so on. So you've got your squares. Let's find the weird ones. Fibonacci sequence. We will talk about Fibonacci sequence maybe on Friday. But if you add up in this direction, you get Fibonacci numbers. How many people know about Fibonacci numbers? Like show of hands or.
Touched on it briefly in 120.
Cool.
Heard of it.
All right, we will play around with these either Friday or Monday, and they're a really cool area of science and nature and mathematics, and they'll come to us in the form of recurrence relations, and we'll tie them back into induction, and eventually we'll use these in CSE215 in something we call dynamic programming. And yes, they are related to the golden ratio, which is related to everything. It's music, it's art, it's architecture, it's all that good sort of stuff.
Isn't so Fibonacci is like you start with 1, it's 1, or start with like 1 plus 1 is 2, then 1 plus 2 is 3, and then 2 plus 3 is 8.
Yeah, so Fibonacci numbers, it's a sequence of numbers, and it begins with a pair of 1s. So let me go ahead and tag this. Begin with a pair of 1s, and the next number is just the sum of the two numbers before it. So 1 plus 1 is 2. If I want to find the next number, it's just 2 plus 1 is 3. The next number will be 3 plus 2 is 5. Next will be 5 plus 3 is 8. And you just keep doing this. So each number in the series is the sum of the two numbers right before it. And it's a beautiful sequence that pops up in a lot of different places. In if you pick up a pine cone and you start at the middle and you follow a spiral out and count how many little sections of the pine cone there are, it's part of the Fibonacci series. And as you move further from the center, the number of pieces of the pine cone increases, and if you count those on each concentric spiral, you get the Fibonacci sequence. And there's reasons for that. And if you look at a population of rabbits growing under certain idealized conditions, the population grows according to a Fibonacci series. This was, I think, how it was actually discovered originally. It wasn't studying population growth. And we'll reproduce that in class next week probably. So you can find Fibonacci numbers inside Pascal's triangle. This one is really weird. Finding how many ways you can partition a polygon into triangles. So a triangle can be partitioned exactly one way because it's a triangle. A square can be partitioned 2 different ways. A 6-sided polygon can be partitioned 14 ways, and so on. And you can find those numbers in Pascal's triangle, subtracting the number adjacent to it. So 2 minus 1, 6 minus 4 is 2. That's 5. That's 24, and so on. Or 14. Binomial expansion we talked about. Mandelbrot sets and fractals and Sierpinski's triangles and all that sort of stuff. So that's Pascal's triangle. I've heard that there are some things in nature that do not follow Fibonacci sequence. Other than humans, probably. It's probably interesting to study what the characteristics are of something that doesn't follow that. It's also interesting to note that humans follow all kinds of predictable patterns, even when they're acting independently. Just like, a swarm of ants will obey certain statistical laws, just like gas particles do, just like cars on a highway do. Even though, you know, there's intelligent control going on behind the decision making, these patterns still emerge sometimes. But yeah, the ones that don't follow that, I think those would be interesting to study. So this would have been a great Friday lecture because we're ending with like the really weird stuff, but it's kind of like Friday because we get tomorrow off. So, but anyway, that's sort of the conclusion of this this unit on counting. So the main punchlines are, you know, product rule, sum rule, principle of inclusion, exclusion, and then the pigeonhole principle, which we saw some examples of, and then today we mostly did combinations and permutations, unordered and ordered arrangements of objects. And so look at the homework problems, right? Those are posted. Play around with those. Bring questions on Friday to class. But they're really just problems about, you know, taking some question and trying to imagine it in terms of these concepts that we've been working with. And as always, right, the goal is to try to strengthen our understanding of these concepts by using some specific examples and working with particular problems on them. So don't get bogged down by the math, right? But play around with, you know, trying to re-envision these problems in terms of these concepts we've been doing this week. So we'll talk about homework 6 on Friday. We'll go over any questions you have for homework 7 on Friday. And then we're going to start the next part of this course, which is looking at something called recurrence relations. And this will be Fibonacci series, and we'll look at bacterial growth and geometric series, things like that. And then after all of that, I mean, we're coming to the end of week 8, so we have basically 3 weeks left, and we miss, you know, 2 days, 1 week for Thanksgiving. So we really got about 2 weeks left, right? Which is like 6 classes. So we'll spend some time on recurrence relations. We'll spend probably 2 classes on that, and then we're going to go ahead and talk about some graph theory, and then talk about some automata theory. Look at natural languages and Turing machines and questions about Turing machines, NP completeness, and some other weird stuff like that we'll end the course with. So we're coming into increasingly weird and I think interesting stuff. But that does us for today. So go ahead and send me an attendance ping on the way out. Have a great afternoon. Have a great Veterans Day tomorrow, and I will see you on Friday.
Just out of curiosity, you said we're missing 2 days for Thanksgiving. Is that Thursday and Friday, or do we not have a class on Wednesday?
So Clark gives you off Wednesday, Thursday, and Friday. So for 215, we'll miss 2 classes.
Okay, so we'll only have a Monday that week.
Yeah.
Okay. Thanks. Have a good day.
All right. You too. Have a good one.
Bye-bye.